A traveler wants to minimize transportation time. Fermat's principle in optics state that light follows the path that takes the least time. In this section and the next, we solve such problems as maximizing areas, volumes, and profits, and minimizing distances, times, and costs. In solving such practical problems, the greatest challenge is often to convert the word problem into a mathematical optimization problem by setting up the function that is to be maximized or minimized. And so, as Evan said, we've done this kind of stuff before, so we're going to start by recalling the problem-solving principles discussed on page 54. So this is the thing that we did this already, okay? So first thing, understand the problem, always a good place to start. Second thing, and this is the thing that a lot of math kids are bad at because you're so unbelievably lazy, is to draw a diagram so you can see what's going on. And I know that takes like 10 seconds to draw a rectangle and put an X and a Y on there, but it's, yeah, I know, too far. Number 3, introduce notation. So you get your different variables and all that kind of stuff. And then a lot of times this is the step here where you're going to have 2 equations. One of the equations is going to be the one that you're trying to find the maximum or minimum for, and then the other one is going to be an equation based on some given restraints. So what you're going to do is you're going to take and solve the equation, for one of the things, and then substitute it in to the other, because we don't want to take the derivative if we have more than one equation involved. Okay? So here we go. Example number 1. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river.
Every river is straight.
Every river is straight. He needs no fence along the river. What are the dimensions of the field that has the largest area? So there's the river, and so he's going to make a little helio here. This is the river underneath. The river should be blue probably, huh?
Yeah.
So here is the river, and here is the field. All right? Now, we all know that none of these problems that we're going to do are problems that anyone would actually do in their real lives. Okay? The problems that people actually do for their jobs that involve calculus are way too complicated for you guys to solve. Okay? Yes, and so they make fake ones because they have to try to simplify it to a way that you guys can understand. So you don't need to point out to me that rivers aren't usually straight, or that farmers don't usually use calculus to fence their fields. I get that. They're just trying to give you sort of a little bit of a taste, okay?
What this doesn't make, let the field dimensions already be set.
Right. Okay, so what are we going to do? How do you want to label the sides? X and Y. How creative, Mary. And so it says, what are the dimensions of the field that has the largest area? So what's the area of that field? X times Y. Okay? But we got 2 variables there. We don't want 2 variables. So what we need to do is we need to come up with a relationship between X and Y that uses the 2,400 feet. What'd you say, Connor? Okay, since the perimeter of the fence is 2,400 feet, we also know that 2x plus y equals 2,400. Okay? So, how can I take that second equation and solve it? Plug it into the substitution, elimination. You want to solve for y? Okay, good plan. So y equals 2,400 minus 2x. So that makes our new area equation, area equals x times 2,400 minus 2x. Okay? That is the one, the equation that we want to maximize. How do we find the maximum? No. Take the derivative and set it equal to 0. Okay? So So before I take the derivative of this, I'm going to distribute the x so that I don't have to use the product rule. And I'm not going to pull out a 2 because it's not equal to anything yet. Okay? I'll pull out a 2 when we set it equal to 0. Yeah. So now I take the derivative, and if this is a derivative that you can't take, you really probably should just get it. What's the derivative? 2400 minus 4x. Okay? All right, now I need to set that equal.
I can do that.
Now I need to set that equal to 0. So if 2400 minus 4x equals 0, then that means x equals what? 600. All right. Now, you know, because they're asking us for the maximum, that that answer is going to be the maximum, okay? But for the 5 of you in here that are going to take the AP Calculus test, you need to justify that this is a maximum, okay? So you could do a sign chart, all right? But you could also, in this case, use very easily the second derivative test. What's the second derivative of this? -4. And since the second derivative is negative over the whole domain of this function, what does that say about the function? Concave down, which means that this is a maximum. Okay? Okay, or you could do a sign chart, and if you did a sign chart, you would say, we came up with x equals 600, pick a number, plug in 1. So since at 1 this is positive, that means over here we're positive, over there we're negative, which again means that this is a maximum. Okay? So depending on which is easier to do, plug in numbers or take the second derivative, you want to use either the first or second derivative test. What the second derivative test is? If the second derivative is positive, then that means it's concave up like this, which would mean it'd be a minimum. And if the second derivative is negative, that means it's concave down like that. Right. So that's how we know that it's maximum. Okay, so if x equals 600, then y equals what? 1200. You get that by plugging x into there somewhere. And so those are the dimensions of the field that will give you the maximum area. Okay? And yeah, you've done this probably in some form. Ever since I think you first looked at it in geometry.
I just wonder, like, how can you get a smaller area?
Well, if you tried some numbers, you'd
Yeah, I would understand it, but I just don't.
conceptually?
See how.
Because it seems like it should always be the same. Because if you take some off of here, you're adding some onto there. Gabe?
Back in ninth grade geometry, you said like the hexagon, like for bees and stuff like that.
Yes.
How do you call it? Like it's the most.
Right, it's you get the most area for the minimum amount of perimeter. I mean, that might not include a circle, but circles no, because circles don't tessellate, so you have gaps in there, so that's how that goes. Yeah.
Maybe farmers should start fencing their fields.
Maybe. All right, number 2. A cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay? So we're going for a minimum this time. We have a drawing already. If we're going to minimize the cost of the metal, what are we trying to minimize? The surface area of the can. So the surface area of this can, everybody remembers their surface area formulas. Pi squared is going to be the area of the thing, and there's 2 of them, right? So the bases are 2 pi r squared. And then you, of course, remember that you get a can by just rolling up a rectangle. And the area of the rectangle is base times height, so the area of the side of the can is going to be also base times height, but the base is the circumference. So that's going to be plus 2 pi r 18. Okay? So that's the equation that we are trying to minimize, but again, we've got two variables, the radius and the height, so we want to find some way to relate those together. How do we do that?
Pull out 9.
Nope.
It equals 1 liter.
Right, the volume equals 1 liter. So what's the volume of the can? Nope. Pi r squared h, area of the base times the height. And so pi r squared h equals 1 liter. How does that help us? What's 1 liter? Right, so we're going to use it, but what's 1 liter, like with a dimension, depending when we're not European here? A liter is 1,000 cubic centimeters.
So why are we just using 1,000 cubic?
Because this has a physical length attached to it. If we tried to do this, then what would we say that the
Oh,
radius
gotcha,
should
gotcha.
be? Square root of 3 pi meters? Yeah, that's not a thing. Okay? All right, so what do you want to solve that for? H. So that's pretty easy to do. H equals 1,000 over pi r squared, right? Yeah, but we're going to plug this in here first. So our new surface area formula is 2 pi r squared plus 2 pi r times 1,000 over pi r squared.
I'm not feeling
So, let's be honest. I want to simplify this right here. Pi's cancel, this r cancels with one of those, so that's going to be plus 2,000 over r, but let's go r to the negative 1. I went 2 times 1,000.
Good calling that stuff.
Yeah, now we're going to have to use proportion rules. All right, everybody caught up?
That's the negative.
Yeah, that's the negative 1 power because it was on the bottom, but I don't want to use the proportion rule. Right at the top. So what's the derivative of 2 pi r squared?
4 pi r.
4 pi r. What's the derivative of 2,000 r to the negative 1? Negative 2,000 r to the negative second. And now since we're going to do some algebra with this, I'm going to put that back on the bottom. Well, it saved us the time of doing the quotient rule. So. Okay, so what am I going to do with that? Set it equal to 0. All right.
Why wouldn't it be 1?
Yeah, you're going to need 2 equations because you're going to have 2 variables. What view? Why would what be 1? Oh, because we decided that if we set it equal to 1 liter, then our answer would be like the radius is this many liters, and that doesn't make any sense. So we wanted to change, we wanted to use the fact that 1 liter is 1,000 cubic centimeters, so we can get our radius in a dimension that is actually useful. Okay? All right, how do I solve this? I don't like this right here. Nobody in the room does. How do I get rid of it? Multiply everything by r squared. So 4 pi r times r squared is 4 pi r cubed minus 2,000 r over r squared times r squared. They cancel. And 0 times r squared is 0. Okay? So, using the technology available to you, please solve this for r. Add 2,000, divide by 4, divide by pi, take the cube root. If you're going to divide by 4 pi in one step, please remember to put the 4 pi in parentheses so it divides by both of them. You take the cube root, or you could raise it to the 1/3 power. No, because we're manufacturing the can, so we need to know.
I found I can't.
Go to the 1/3. What? What did he get? 5.4193.
Yeah.
Okay, so that's the radius. How would you use the radius to figure out the height? Plug it into this equation right here. How do we know that this is a minimum? You can take the second derivative of this thing right here and then plug this number in and see that the answer this time should be positive if we want a minimum. Or you can use a sign chart. So if I plug 0 into here, then that gives me a negative answer, right? And so that means to the left of this answer is negative, to the right is positive. So since it's going from negative to positive, that also means that it is a minimum, okay? What did you get for the height? 10.83. Okay, so you're the engineer, you figured this out, so the specs off to the manufacturing people, and they make you some cans. Yeah. All right.
You know they make guns out of the 3D printer?
I saw that. Yeah.
Like they don't have the
Can
metal
you make a
shipping?
3D printer out of a 3D printer?
That's
Well, then how do they make their 3D printer?
Not with a 3D printer.
They have chocolate 3D printers.
gross.
You know, it sounds so weird.
Yeah, I saw that. Like,
Pumpkin.
how does that work? Like, they just put the ingredients in the chocolate and then it's actually like cocoa beans.
Can you design like chocolate houses with it?
Yeah.
It's really awesome.
Okay, next one.
I know.
Find the point on the parabola y squared equals 2x that is closest to the point 1, 4. So here's the parabola, and it's a y squared parabola, so that's wacky. But we're big kids, we can handle functions that aren't functions. Correct. And then here's our point 1, 4, so we're trying to find the point on that parabola that would be the closest to that point, okay? So what you're trying to do is you're trying to minimize that distance. So start thinking distance formula.
Hang on.
Try and find it. Yeah, rack your brain for a little
It's
bit.
Y.
Are you writing it down? Are you writing it down?
Because you said like spaceships, so I was thinking about last time on news, where there's a Russian spacecraft that they found activated after 3 years, and they're gonna try to send it to a probe on it.
Oh, really? And are they gonna try and like bring some stuff back from it, or are they?
I don't know what they're planning on doing.
When I was in high school, we went and heard a guy speak, and so this is kind of funny to think about because that's a lot of years ago. 1985, so almost 30 years ago, I think. We went to hear a guest speaker, and he was talking about mining meteors or comets or whatever.
For their material.
Yeah, and 30 years later, how we started that.
They said that was going to happen in 30 years.
Yeah, he said that's going to be because they're so mineral rich that's going to be the way.
That could be a thing. I mean, it's a thing in Star Wars. That one place they said
Right.
that one chick too when she was diamond.
So, yeah.
Yeah, I think that's Star Wars.
Hey, shut up.
Right.
Real parent to Star Wars.
Then we'll
There's
attach
companies that because hydrogen and oxygen is the most like powerful power.
Oh, right.
Yeah, so
You
spaceships
guys
in
do,
outer space
right.
are already empty. So
Yeah,
they
but
want to
fuel
start
up
like
and
their own
then-
refueling station.
All right, so who's got the distance formula for me?
It's horrible.
Anybody?
X2 minus X1 squared.
x2 minus x1 squared plus y2 minus y1 squared, and then you take the square root, right? Because it's just the reverse of the Pythagorean theorem.
Okay.
So what we are going to do is we are going to use a point on this curve x comma y as our x2 and our y2, and the point 1 comma 4 as x1 and y1, or we can go the other way around, it doesn't really matter. So any point on this curve the x coordinate is going to be x, what's the y coordinate in terms of x? No, just totally ignoring that, just thinking about this curve right here. If I gave you an x coordinate and said, what's the y coordinate on this curve that goes with that x, what would you do to find it? Right, here's the relationship between all the x's and y's on this curve. So if I told you x is 5, what's y? What would you do? Plug in 5, which means you go times 2, and then square root it. Right, okay? And we know from our diagram here that we want to be on the upside of here. So we're going to take the positive square root. So our y coordinate is going to be the square root of 2x. Okay? So the distance in this case is the square root of x2. So I'm just going to use that as my x because I like to have the variables first. It doesn't matter. I can pick any spot on it. Minus x1. What's x1? 1 squared plus y2, which is square root of 2x.
It's the point.
It's this thing right here. So my y point is going to be 4 minus 4 squared. Okay? And what do we need to do with that? Take the derivative and then set it equal to 0. Now, do they really want us to take this nasty derivative? That's their question. Yeah, it's pretty terrible. Oh, they did it, they solved it the other way around. It's okay. Okay, so what we're going to say is we're going to go look. The minimum of this right here is going to happen at the same place as the minimum of that.
I would agree.
You agree? Right, we're going to take away the square root. And that's going to make our work considerably easier. Okay? So we're actually finding the distance squared. What?
I said, what's that? Yeah, like stone.
Okay, what's the derivative of this?
You can deserve it.
2 times x minus 1 to the first. Then technically I'm using the chain rule, so I'd have to, take the multiply by the derivative of that stuff, but that's just going to be 1, so it's not going to matter. Plus the derivative of this, which is going to be a little trickier because of the square root thingy in there. So I again put the 2 in front, times the square root of 2x minus 4. Now I have to go times the derivative of the stuff inside. So what's the derivative of 2x, all of that to the 1/2? I'm going to put the 1/2 in front. I'm going to make this 2x to the negative 1/2 times the derivative of the stuff inside, which is 2. So the 1/2 and the 2 cancel. So it turns out the derivative of the square root of 2x is 2x to the negative 1/2. Yeah, that's the derivative of the distance squared, right? Which we're going to just say that that's, again, the minimum of that is going to be the same as the minimum of this. Okay. All right, so what do I have to do with this? Set it equal to 0. Do you want to see the fun algebra? No? You feel like what? You feel guilty if you don't do it? You could do it? Okay. You solve that and you get x equals 2. Is what you get if you set that equal to 0. Not really quite seeing how that works, but I'm just going to pretend since the book says so that it does. And so now if we plug 2 into there, 2 times 2 is 4, square root of 4 is 2. So the closest point on that parabola to 1, 4 is 2, 2. Good job?
Yeah, it's right there. It's basically,
Yeah, kind of.
it's pretty close.
Pretty close, yeah. Yeah, with my, right, what's that?
That's not gonna be on there.
Okay, let's stop there and give you guys a few to work on before we do some more complex ones.
Me and Em this time has some kind of
What do you say?
No, we just don't have anything to correct before we get back.
Well, when I, yeah. No, when I saw that next example, I realized that that's pretty complicated, so, let's stop.